Okay, cool. So I share a talk with Sebastian Nehrdich, and our talk addresses the question how we can label Vedic texts with syntactic dependencies and which methods are best suited for this task, and also which linguistic and philological conclusions we can draw from the data. The presentation has 3 parts. In the first part, I will talk about the basic annotation process and the current coverage of the Vedic tree bank. In the second part, Sebastian will tell you something about recent advances with the help of deep learning. And in the third part, I will present again some linguistic and philological conclusions, some very preliminary ones. So what's dependency labeling? Dependency labeling means that we label all words in a sentence with their syntactic functions and establish connections between the words. This means the syntactic edges. And as an example, consider this sentence here, the first sentence from the Veda. The sentence has one so-called root word. This is ide, in this case, the verb. This is the root. And this verb has a direct object, agnim, the god he invokes, the speaker. And therefore, you draw a label between an arc between ide and agnim and label this arc with the label object. And now agnim again has another apposition, a nominal modifier, an apposition, purohitam, and you draw an arc from agnim that goes out to purohitam that indicates in which relation they are. Of course, you can have many and long discussions about how to label them and how to draw the arcs, but this is a basic process. My example here is a very simple short sentence, but you can imagine, for instance, in the Brahmana, Shatapatha Brahmana, a sentence may have 50 or 60 words, so you get really long and complicated constructions here. So we use, for our labeling, we use the tag set of the universal dependencies. These are kind of standard nowadays in natural language processing. And we also designed our own annotation guidelines. So we did this in cooperation with the University of Zurich and with Erika Biagetti. And these annotation guidelines cover critical cases and difficult constructions that are mainly constrained to Vedic. And it's about 70 or 80 pages nowadays, quite richly illustrated. And you can find these guidelines here under this web address. This is a permanent link, so you should get access to it. So we perform our annotations directly in the interface of the digital corpus of Sanskrit. And here, for instance, you see the first 2 sentences or first 2 lines from the Kataka Samhita, a text on which we cooperate with Kyoko's group in Kyoto. And you see here, for instance, the first sentence, Prajapati is labeled the subject of the root word idam, a pronoun. Idam is modified by a discourse particle, and it also has the verb as a copula. The annotation is built on top of a machine learning background. When we want to create a link between 2 words in a sentence, you take one word and you take the second word, here these red squares at the bottom, and drop the child word on the head word. And in this moment, you see a pop-up dialog. And in this dialog, which you see, sorry, my mouse is not doing what I want. You see it here in this dialog. You have a list of universal dependency labels. And please note that these labels are sorted by some number here in the brackets, and the highest number is at top, and then the numbers go down again. And this ordering is the output of a machine learning algorithm. So basically, we reorder the list of all possible universal dependency tags using a kind of very simple neural network. How does this work? When the annotator chooses a head and independent words, the neural network collects some information about the linguistic context and about the words itself and about the sentence context. This information is fed into the network, and then at the end you have a so-called softmax layer, which means multi-class logistic regression. And this produces a probability distribution over all possible UD labels that could apply in this case. And this output of the neural network is used to sort this list here. And you can read more about this in a paper from 2020. And there we also reported some accuracy scores. So for instance, we got an at3 accuracy of 95%. This means that in 95% of all cases, the best or correct label is found among the top 3 labels here in the list. This is, of course, I find it at least quite useful because you don't have to scroll the list. And this, of course, reduces time you need for annotation. And I think it also reduces the error rate and the disagreement between annotators because the classifier learns from the data of all annotators. So the last slide in the introduction gives you a brief overview of the coverage, of the current coverage of the Vedic tree banks. This is a bit outdated. Nowadays we have, so here you have the number of sentences and here you have the number of words grouped by some traditional classes of the Vedic literature. And you see that most annotations come currently from Samhita texts and from the Brahmanas. As I said, this is a bit outdated now. We now have about 19,000 sentences, and you can get the current dump of the whole data under this web address. This was just updated a few weeks or 2 weeks ago, so this is really up to date at the moment. And one point you can, of course, see is that late Vedic, here, for instance, Shrauta Sutras and especially Dharma Sutras are strongly underrepresented. And in the second part of the presentation, Sebastian will address the question how we can use deep learning for speeding up the annotation, for instance, for such underrepresented parts of the Vedic tree bank.
Okay, yes. So first of all, regarding the background of dependency parsing, generally speaking, dependency parsing is the process of analyzing the grammatical structure of a sentence by determining the relationship between the head words and the word that modify those heads. So basically, we are building a tree structure at this point. And there are 2 parsing methods widely used nowadays. The first is the transition parse based version, and the second one is the graph-based version. And we found out in our research that graph-based parsers show generally better performance for morphologically rich Indo-European languages and for those of the subject, object, verb types. So previous research has also shown this for other languages. And since Vedic has both characteristics, we decided to base our work mainly on the graph-based parser. Okay, maybe next slide. Yeah. Coming to the parser design, we adapt the B-affine parser of Dotsad and Manning since it achieved state-of-the-art UAS on all Conlu 09 languages and because it has a better performance on non-projective languages. And on top, to this model, we add a character-based CNN from the DCST model, which is another parser. And this works on the inflected form, and we also integrate a larger number of categorical input features. These are morphosyntax, verbal nouns, inflected word forms, punctuation, and text historical layers. And then we also augment the training data by randomly concatenating up to 4 not necessarily subsequent sentences from the training set. So there's more data available. And then in the paper, we also evaluate the effect of deep contextual embedding models, such as Elmo and BERT on the B-affine parser to see how if they can improve the model or not. And of course, other parsers for Sanskrit, such as Kulkarni 2021 or Krishna et al. 2020-21 exist, but the application to Vedic is not promising since they either rely on the Paninian system of grammar or they are trained on a rather small corpus of Neo-Sanskrit and thus don't perform satisfyingly on cross-domain tasks. So this is why we decided to build our own system. Okay, next slide. Yeah, coming to the parser performance. Among other available tree banks of pre-modern languages, the situation of Vedic is probably best compared with that of Latin and Ancient Greek. And here in this table, we give the results from the PO-IEL corpus for both languages, because the coverage of material within that corpus is most comparable to the Vedic tree bank regarding the temporal layers and so on. And what we see here is that actually our Vedic B-affine model is able to outperform the two, the Latin and ancient Greek parsers by a visible margin. Regarding UAS and regarding LAS, it is at least in a comparable region. And just a quick explanation, UAS is basically if the position of the word within the tree was determined correctly, and LAS is if the position of the word within the tree and the label as well are determined correctly. So basically UAS is the easier score to achieve and LAS is the more difficult one. And what we also see in the results is that the DCST model, which has a certain pre-training routine integrated, is not able to perform better than the basic B-affine model. So this we found interesting to note. Okay, maybe next slide. Yes, coming to the lexical embedding strategies. In this table, we present the results from fast text, which is a static model, which we already discussed previously in the other presentation, and also Roberta Vedic, which is a model. Roberta is basically a contextual model which uses a lot of resources in order to be trained. And so unlike fast text, which is done quickly and can be even calculated on a laptop within a few minutes, a Roberta model requires a large GPU and a lot of time in order to be trained efficiently. And we used for both models, we used the entire Vedic corpus that we have at hand, and also additionally the Gretil Sanskrit data in order to make the embeddings more robust. And among the contextual models, the Roberta model with the Vedic and Gretil data was the most performant one. And what we see here is that if we have no additional linguistic information, basically the first layer of the table, we see that the contextual models perform better than the static models. And this is actually a considerable margin. In the case we have only a part of speech tag available from the universal dependencies, we see that the margin between the two models is getting smaller, but it's still better performance on the side of the contextual models. And if we have all linguistic features that we included in our model available, the static fast text model is actually performing better than the contextual model. And here our assumption is that probably because of the lack of training data for Vedic, because it's a comparatively small corpus and the transfer learning from Sanskrit into Vedic does not yield to perfect results here. So we assume that this is the cause why contextual models for Vedic do not perform as well as expected. Okay, next slide. Yeah, coming to the conclusions about parsing, the performance of the B-affine parser on the Vedic tree bank is superior for UAS and on pair for LAS with the current state of the art for ancient Greek, for IEL and Latin. The larger number of categorical input features and the augmentation of the training data lead to decisive performance gains. And the additional pre-training performed by the DCST model does not lead to clear improvements. And contextual embedding strategies, while being very expensive to train, show a visible performance gain when no or little linguistic information is available. But as soon as enough annotation data is available, static embedding strategies in combination with the full ensemble of linguistic informations are finally superior in the case of Vedic. Yeah. And next slide. Yeah, just to show you the annotation pipeline that we came up. So first we have the input text, and this is then pre-processed by the tools available in the DCS. For example, word segmentation, stemming, part of speech tagging, grammatical annotation. And in this stage, there's also manual post-correction involved in order to make sure that the results are as good as possible. And this data is then fed into the dependency parser that I just described. And once this parsing tree is proposed by the parser, we once again use manual post-correction via the interface of the DCS in order to correct the mistakes that the parser made. And this corrected data can actually be used to retrain the parser. And in this way, the quality of the parser is improved So the more post-corrected data we have available, the better the performance of the parser gets, and we have to do even less work on annotating the parsing trees. So the more help we have, basically, the more people who are involved in order to improve the parsing trees, the better the output will be, and the less work has to be done in the future. So this is a process that stimulates itself, basically. Yeah. Okay, that is all from my side. Yeah.
Okay, so I jump in again. So in the third part of this presentation, I will try to give you an idea of what kind of research questions we can address when we have these syntactic data. In general, there's surprisingly few work on Vedic syntax. Of course, we have Delbrück's survey from the 19th century, but Delbrück is largely concerned with case syntax and the function of particles. And apart from this, we have a large number of studies that deal with quite limited and small aspects of Rigvedic syntax. So not Vedic in general, but only the Rigveda. And these papers often have a very strong focus on how the context influences certain constructions. In my opinion, what is missing is for instance, large longitudinal studies of word order changes or changes in the general structure of Vedic sentences. And we also need studies that somehow substantiate their claims using quantitative corpus data. So if you're interested in these and related problems, you can have a look at this publication by Hans-Heinrich Hock, Issues in Sanskrit Syntax. This is quite nicely and concisely described. So what can these tree bank data tell us about developments in Vedic? In a paper that will come out this year, Sven and I addressed one of the numerous open questions, namely how objects, so direct objects, are placed in relationship to their governing verbs. There's an ongoing debate among Vedic scholars if Vedic displays a trend towards subject-object verb placement, and if early Vedic has a substantially freer word order than later text, and to which degree, for instance, the register, the means prose-verse distinction, influences such distributions. So we took the placement of direct objects as one sub-problem from this field, and we assessed what the data from the Vedic tree bank can contribute towards its solution. So in total, we extracted about 5,300 verbs in main clauses and their direct objects. And we assigned each of these constructions to one of 5 diachronic layers in a system that is based on previous research by Witzel and Kümmel. And we also determined the animacy type of each object using word semantic information from the DCS. This was important and relevant because many scholars claim that animacy influences the placement of words in a sentence. So this table you see here gives you an overview of the composition of our data set. You see that, for instance, register, the first point here, is somehow evenly distributed. So we have a lot of metrical text, we have a lot of prose text. Diachronic layers are already already a bit biased. So we have not so much data from the old Rigveda and quite a lot, for instance, from the mantra period. And the distribution over animacy classes is quite strongly biased. So all these results should be taken with care. So to start with, we performed a series of visualizations and statistical tests of significance. And on this slide, you see frequency bar plots when we split the distances between objects and verbs by 5 diachronic layers. So the layers are here at the top, Rigveda, mantra, old prose, late prose, and sutra language. And here at the bottom, you see the distances. So negative numbers mean the object is to the left of the verb, and positive numbers mean the object is to the right of the verb. And one thing that you can see immediately is that, for instance, placement to the right of the verb is really strongly dispreferred in the later period. So we only have very few objects placed to the right of their verbs after this, starting at the old prose layer. And you also can see that post-verbal placement of objects already gets dispreferred in the mantra language. So this is most frequent here and gets dispreferred here and has completely disappeared here in later layers. However, this cannot be taken as proof for some kind of diachronic development, as we have not taken possible influence factors, confounding factors into account. So let me just mention quickly that animacy interacts with object placement, but it notably does not interact with the diachronic distribution, as can be shown by applying statistical tests of significance. And similar register interacts with object placement because metrical texts show a higher proportion of post-verbal objects than do prose texts. Nevertheless, statistical tests show again that there are still strong diachronic trends, even if we consider the metrical prose split. So to understand what's going on here, we restricted our evaluation to objects found in pre-verbal placement. And as you can see here on the left side, on the slide here, the proportion of objects that are placed directly before the verbs. These are the black parts of each bar. So these are objects placed directly before the verb. And here are the times, Rig Veda mantra, or prose, late prose, sutra. So this proportion constantly increases over the Vedic period. So you get more objects placed directly in front of the verb. And personally, when I saw this plot, I wanted to construct a chronological trend from this observation. But Sven rightly remarked that we should have a look at another factor, namely the number of arguments a verb can have. So if a verb can only have one argument, it's quite probable that this one argument is placed directly in front of the verb. So we plotted these data, and this is, in my opinion, a really interesting outcome. As you can see here, Vedic verbs seem to lose arguments over time. So black are verbs with only one argument, dark gray with 2 arguments, and light gray with 3 and more arguments. For instance, you see here in the Rig Veda, we have almost more than 25% of all verbs have 3 and more arguments, while only less than 10% of all verbs in the Sutra language have 3 or more arguments. So this means that at least parts of the changes in word order may probably be explained by changes in the argument frames of verbs. I think this is a fact that has not been considered sufficiently so far in research. So let me quickly summarize my presentation. Judging from the results we have obtained so far, quantitative syntactic data may really open up new insights in the development of the Vedic corpus. And as Sebastian and I have demonstrated, we have a working annotation interface, we have comprehensive annotation guidelines, and we have parser, which greatly reduces the annotation time. So just to say, if anybody of you is interested in annotating other parts of the Vedic corpus with syntactic data, we would really be happy to cooperate with you. And future work in our group mainly relates to automatically finding interesting chronological trends in these syntactic data. So we have to say that the actual research work has just begun. Thank you.
Hey, thank you, Oliver and Sebastian, for your interesting talk. So we'll proceed to the question and answer time. So please.
Hello.
Yeah.
Yes.
Please go ahead.
So Professor Hellwig, thank you for the very interesting talk. Towards the end, you presented these verbs that are losing the objects. But very interestingly, the proportion of verbs that are having 2 objects remain almost the same. So basically, that means that verbs that had got 3 objects, are they getting transformed to verbs that are having only 1 object, or the verbs getting 3 to 2 and 2 to 1 is at the same proportion?
This is, as I said, the actual work has just begun. So this is basically what we have now is just a survey study. And of course, you should now start to look at the actual works and at the actual passages that come up there. And I hope we can answer your question in 1 year.
All right. Okay. So is it fine if we contact you regarding this? You also said collaborations are most welcome. So
absolutely, I would really be happy. Yeah.
All right. Thank you.
So the next question is from the Leza. Yeah, please go ahead.
Yes, thank you very much for the interesting presentation. My question is about the border of sentences. How did you mark the end of sentence? Because, as you know, it's a problem in all languages that we do not have the punctuation, and we are dealing with a problem in the syntax of the Middle Persian as well. Therefore, it would be interesting to know how do you manage this question.
Could you just, because I had to tune up my speakers, could you just repeat the very first sentence of your question?
For sure.
Didn't hear it.
The question is the border of the sentence. How did you?
Okay. Yeah. So basically, this is an absolutely intriguing problem, and it's really complicated. And we have not. We take resource to official translations and see what comes out there and how previous translators segmented the sentences. But this is really extremely complicated, and we just published a paper that discusses these aspects for the Vedic tree bank. So yeah, it's really blows away your mind. So
it would be great if you could put the bibliography of this article in the chat. I would be very thankful.
Yeah, sure.
Thank you.
And I'll do it in a second.
Okay, so the next is the Mahesh.
Yes. So I have a question. So it was mentioned that Elmo embeddings, a point was mentioned, but I haven't seen the results. That was the first point. And the second is, if it was mentioned that the pre-training on the entire Sanskrit wouldn't work, especially regarding Roberta. So can you elaborate on it? I mean, have you tried it, or is it just an intuition?
Sebastian, could you take over? Or
yeah, I'm not entirely sure if I understood everything correctly, but just to explain again, we did use all the available Vedic and Sanskrit data to train Roberta. And I think we ended up with something about 300 megabytes, maybe a little bit more. The exact number I don't know at the moment. And so actually we used as much data as we can get our hands on. And as is visible in other papers that deal with the performance of Roberta models on smaller corpora, 300 megabytes is something about the threshold where the models start to become superior. If you have less than 300 megabytes, it is becoming difficult. And in the case of Vedic, of course, this is basically a subcorpora. We don't have 300 megabytes of Vedic, unfortunately. We have much less, maybe only one tenth of that. So yes, our observation at this point is that the size of the Vedic corpus is not sufficient to create a model that always performs better. But if the resources are restrained, it is still helpful, and it still performs a little bit better than if you use static models. So there is an improvement, but as soon as your corpus is richly annotated, that improvement is disappearing. Yeah.
So my exact question is the Roberta pre-trained on the entire available Sanskrit corpus?
Yes, it is.
And then it's fine-tuned on the Vedic corpus.
We tried both. Basically, what happens if we first train it on Sanskrit and then fine-tune it on Vedic, or if we train it with both data available from the beginning. And I think the observation was that the difference is not significant in that case. And we also used the XLM Roberta, the big one, which has about 100 languages, which also includes Sanskrit. And we fine-tuned that on a Vedic specific corpus. But the results were not that good as compared to only taking Sanskrit and Vedic data.
Okay, thank you. That answers my question.
Okay, so is there any comments or question?
Can I ask a question?
Yes. Go ahead.
Thank you very much, Oliver. and Sebastian. I want to ask about the segmentation or period of the text. You have a 5 period for the
5, yeah.
and the Rig Veda and then mantra.
So you ask about the second one, a mantra layer, or
Mantra, yeah, and does this mantra layer include prose mantra and also metrical mantra?
it's main? No. It's
Oh.
So it's basically the allegedly later parts of the Rig Veda. So no family books, but 1, 10, and whatever. It's Atharva, and it's the mantra parts of Yajurveda.
I think this is a little bit problem because so Yajurveda mantra and also Atharva Veda include prose text, and I think it is important to distinct prose language and metrical language.
Yeah, absolutely. We do this. We do this. So for Atharva Veda 15 is old prose, so it's not mantra.
And so can we use this analysis to smaller segmentation? So can we or I want to segment the text into smaller segmentation, and if we can use this as analysis to this smaller segmentation, then do you think that does it work?
It should be possible, yeah, I think so.
Yeah.
So we have to come to terms where to make the splits. So
yeah. So shall we try? So, thank you.
Okay, thank you everyone. And the program is behind on the schedule. So let's thank you again.